Hello, welcome to 6502 Assembly Programming. This is a brief introduction to the 6502 microprocessor and writing assembly for it. This isn't going to be a comprehensive class or set of videos on the 6502, nor is it going to teach everything about computer architecture, but it's going to give the basics to get most people started in writing assembly for the 6502. First disclaimer is this ish slide. If you look in the top right corner, I have this little red button that says ish, and I've put these on slides where I've made some general simplifications or generalizations that aren't completely accurate, but are done to help facilitate understanding of main concepts rather than trying to teach exactly how it is and some of the important details being lost in some of the specifics. So if you see this ish tag, know that some of the things that I'm discussing aren't 100% accurate, but you're getting the main ideas. Alright, so episode 0, Basic Mathematics and Computer Science. So before we write any assembly or talk about the 6502 at all, we need to understand how mathematics works in a computer. There's this joke that programmers have on shirts from time to time. You'll see people walking around with them. Probably not often if you don't work in an engineering field, but I don't know. I've seen a few. And it goes like this. There are 1-0 type of people in this world. Those that understand binary and those that don't. And we'll see how that matters later and what this joke actually means. Alright, so when we talk about math, most people in school, everybody in school I think, learns what is called base 10 or decimal. And I know a lot of mathematics classes, even through high school, don't even address the topic that they're teaching in base 10 or that there are other bases that exist in mathematics. I know that I wasn't taught this until high school, and yeah, it was surprising to me when I learned it that this wasn't mentioned earlier. So what does base 10 mean? It means that each digit of the number represents 10 possible values before rolling into the next digit. So those possible values are 0 through 9. And then when you reach the 10th digit, it rolls over to the next place. Obvious, right? You learn it in elementary school or even before. So, the number sequence 0, 1, 2, 3, so on and so forth until you get to 8, 9. And then on the next digit, it rolls over to the 10th place. You increment or increase the tens digit by 1. And then you reset the ones digit back to 0. And then you continue again until you get to 19. And then you roll over and you increment the 10 digit again and reset the 1 digit. And you just keep on repeating that until you get to 99. And then you roll over the 1's digit, which causes the 10 digit to roll over. And so you increment the 100's digit. And since we rolled over the 10 digit and the 1's digit, it's now 100. So there are 10 numbers in each place. And so each digit represents 10 times the last one. So you have the 1's digit, or the 1's place, the 10's place, the 100's place, and the 1000's place. And I know you're like, alright, go ahead, skip forward. I understand how to add, dude. But it's important to understand the way you understand math now and how it works, so that when we change it, it makes sense. So bear with me for a second. So each of these places, like we mentioned, are the 1's, 10's, 100's, and 1000's. Alright, so if we want to convert from any other base number to base 10, how do we do this? The first thing we do is we take we're going to convert in this example from base 10 to base 10, which is not a conversion at all. But again, it's kind of showing you the basics of math so that when we do use a different base, it's obvious why it works that way. So in the thousandths place, you take whatever number is there and multiply it by 1,000. Then in the hundreds place, you take whatever number is there and multiply it by 100. Same thing for the tens place. Same thing for the ones place. And then you add those numbers together, and you get 4,107. But that's how you get that number. You multiply the value at the place times the value, the weight of that place, and then you add those all together. And that same sequence is going to hold true for any other base. But it's important to understand how we form those numbers. Base 10 addition. Again, yeah, stick with me so we can move to other bases more easily. But we're going to cover, how math works in base 10. So 47 plus 14. What you really do in your mind is you add the ones places, and if there's a digit that carries over, if it goes past 10, you remember you take that number and you add it up here on the top. At least they did before, like Common Core stuff, and now they use I don't know what to add. But this is the way we did it back when I was in school. So you add the ones digit, you carry over to the tens digit, and then you add the tens digits together. So here 4 plus 1, and then you add the carryover as well. So another plus 1, and you get 6 there. And so you get the answer of 61. Right? So you add each place together individually. Base 10 subtraction works the same way, except we're going to borrow now. So 47 minus 18. You subtract the two numbers in the ones place, and if you borrow, then you decrease the value in the tens place by 1 and move 1 over to the ones place, making that a 17 now instead of a 7, so that you can subtract 8 from 17 to get you 9. Basic math. And then you go over to the tens place and subtract the 10 place numbers together. So then you end up with 47 minus 18 equals 27, because of that borrow step that we have in between. Again, this is important because it's going to work identically when we move to different bases. But important to understand how, the stuff that we do every day intuitively actually works. All right, so now the promise. Let's work with a different base. We're going to work in base 2 first. Base 2 is called binary. So in base 2, just like base 10, each digit has 2 possible values instead of 10 possible values before it rolls over. And the digits are 0 and 1. When a rollover occurs, it resets the current digit or place and increments the next one, just like we did in base 10. Works identically. So here, we start out with 0. We increment the ones digit, and it goes to 1. Then when we want to increment again, it doesn't go to 2, because remember that there's only 2 possible digits, 0 and 1. So when we increment 1, it rolls over to the next place. So we increment the next place, and then we reset the current place. So this is 2 in binary. Whoops. And then the next one, we increment the bottom ones digit, and it goes to 1, 1. So that's 3. And then when we want to increment again, well, we only can do 0 or 1, so we have a carryover. And then this is a 1. It can't go to 2, so it carries over. So we have a 1 in the front, and the 2 other places reset. So then you have 1, 0, 0. And this is a 4 in binary. And so on and so forth. You can see the pattern continues. So it works just the same that tens does, but instead of rolling over after 9, you roll after 1. And the other important part is the weight of each place. So in binary, the weight of each place is 2 times the last digit instead of 10 times the last digit. So you remember in decimal, the places that we had were ones, tens, 100s, and 1000s. They're 10 times the last place. In binary, each place is 2 times the last place because we have 2 possible values. So we have the ones place, the twos place, the fours place, the eights place, the 16th place, and so on and so forth, as you see here. So if we take a number, each number in binary, we were talking about bits. A bit is a single either 0 or 1. And in computer science, we're going to call a byte a grouping of 8 bits. And that creates the fundamental unit of math on many machines, or some machines. We'll talk about that in a bit later. But let's look at the base 2 math now. So if you had a number and you wanted to convert base 2 to base 10, so let's say we had this base 2 number right here, 1101. What is this number in base 10? We do this conversion the same way we did before with the base 10. Remember the 4107 example? Let's do it again. So here, this is the 8th place, and there's a 1 here. So we have 8 times 1 equals 8. Next place, we have the 4's place, and a 1 there. So 4 times 1 equals 4. A 2's place has a 0, so 2 times 0 equals 0. Then finally, the 1's place. 1 times 1 equals 1. Just like we did in base 10, you're going to add all these together, and they'll give you the number, 13. So 1101 in binary, converted to base 10, is 13. So the math here worked exactly the same way as we did in base 10. The only difference here is that the value in each place can only have 2 values, 0, 1, and each place is twice the previous place instead of 10 times. So hopefully that makes sense. Alright, so let's say we're converting the opposite way. Let's say we have a number that we want to convert to binary. How would we go about doing that? So we have the number 13 here. How do we convert 13 to binary? You can cheat and go back to the last slide, but let's show you how to actually work that here. So the first thing you're going to do is you're going to do kind of like you do in division. You're going to see how many times each place goes into that number. And in binary, there's really only 2 answers, either 0 times or 1 time. And in this example, I'm starting with the one that happens to work with the 8th place. So how many 8s go into 13? The answer is 1, right? Before it goes negative. If it was a smaller number, say 7, it would go 0 times, and you put 0 in the 8th place. If it was a larger number and 2 8s went into it, then you would need a 16th place here. But for now, forget all that. 1 8 goes into 13. You can only pull 1 8 out of there before it goes negative. So we have 13 minus 8 times 1 equals 5. There's 5 left over, and we put a 1 in the 8th place. All right. So then we hop down to the next place down, which is the 4's place. We have this 5 left over, so that's where we start from. How many 4's can you pull out of 5? 1. So we put a 1 in the 4's place, and we subtract 4 times 1 from 5, and that gives us 1 left over. So we're at the 2's place now. We have 1 left over. How many 2's can you pull out of 1? You can't. 0. So we have 0 times 2 subtracted from 1, we put a 0 in the 2's place, and there's still 1 left over. Then we get to the 1's place. How many 1's can you pull out of 1? And the answer is 1. So 1 minus 1 times 1 equals 0. And so you end up with the number 13 here. This is the decimal 13 up here. This is the binary representation of 13 down there. And so that's kind of mentally how you do that conversion between base 10 and base 2. Actually, any base that you want. As long as you apply that same understanding that each place can hold a certain number of digits, and each place is then multiplied by your base. So in this case, 2 times 2 times 2. Each place is 2 times the previous place. All right. So let's go on to addition. Base 2 addition is no different than base 10. Any of these additions are the same. Just you got to wrap your head around how that carry works. So here we're going to add these two numbers together. Okay? And I'm not even going to tell you what these numbers are. We're just going to go through the math and then we'll see what happens. Just like base 10, the first thing we're going to do is add the first place together. In this case, 0 plus 1 equals 1. 1 is a valid number. Our options are 0 and 1, so we just write it down there, no problem. Next digit, we add together 1 plus 1. Well, 1 plus 1 is 2. But remember that 2 in binary is written as 1, 0, because you can't have a 2-digit. You can only have a 0 or a 1. So we carry the 1 over, and we put the 0 down here, just like we did with decimal, except the carry happens, like we talked about before, after the 1 digit instead of after the 9, because it's base 2 instead of base 10. Alright, so we carry that, we write down the 0 down here. We get down to the next digit, we add the 4's digits together, and it's 0 plus 0, and then you add the carry, so 1, so we put a 1 down here. 0 plus 0 plus 1 is 1, and that's perfectly fine, no roll over there. And on the last digit, we have 1 plus 0 equals 1, and that's perfectly valid, and so we write that down there. Alright, so we have this binary number plus that binary number equals this. And if we look at that in decimal, what these numbers are is this top number is 10, this bottom number is 3, and this and the result is 13. So if you convert each of these manually like we did in the prior slides, this is the H digit, that's the 4, the 2, the 1, so 1, 8 and 1, 2 equals 10 added together. This is the 2 digit, this is the 1, so 2 plus 1 is 3. And this is the 8, the 4, and the 1 digit, so 8 plus 4 is 12, plus 1 is 13. So, yeah, it all works. Doesn't matter what base you're adding in, same rules apply. Yeah, subtraction, very similarly. It's going to work exactly the same, except we're going to again borrow when it rolls from 0. So 1 minus 1 is 0 in this example, and yeah, that works out perfectly fine. No need to borrow there. Next one, we have a 0 minus 1. Well, we don't have any numbers there, so what we're going to do is we're going to go to the next digit and subtract 1 from it. It happens to have a 1, so we change that to a 0 and put your 1 down here, making this a 1, 0, which is a 2. 2 minus 1 equals 1, so we put a 1 in the result. We go to the next digit, which is now a 0 here, so 0 minus 0 is 0. Then we go to the last place, and we have a 1. 1 minus 0 is 1. So those binary numbers subtracted give us this result. And if you're paying attention on the last side, you'll realize those are the same numbers. 13 minus 3 equals 10. So mathematics going the opposite way works all the same. Again, the only difference is, the place rolling over at 2 instead of 10. All right, so a little quiz. See if you can do this on your own. I'm not really going to pause here since this isn't a live session. But if you want to work this out on your own, just give it a quick pause. See if you can convert this base 10 number to binary yourself and see if you get the right answer. So 9 in binary is 1001. We have a 1 in the 8's place, a 1 in the 1's place. 8 plus 1 is 9. And so we have 0 in the 4's and the 2's. So hopefully you got that. All right, so that was base 2, binary. Don't use binary too often in programming, but I don't know. Sometimes you see it, and sometimes it's useful. But it's less useful than what's called base 16, or hexadecimal. You'll see this a lot more in assembly programming than binary. And this is a little bit more difficult to understand, but all the same rules apply. Just like we saw the transition from base 10 to base 2, the same rules apply from base 10 to base 16 or base 2 to base 16. In hexadecimal, each digit can have 16 possible values before rolling over to the next digit. So how do you cram 16 numbers into one digit? And the answer is we start using letters. So we go 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And then once we get to 9, we go to A, B, C, D, E, and F. F is 15. E is 14. And so when you get to F, you're going to roll back over, just like we did before. Just like in base 10, you roll over at 9 going to 10. In base 16, you're going to roll over from F, which is 15, to 16. And you're going to increment the next digit and reset the current digit. All right, so that means, looking at a sequence, we'll go 0, 1, blah, 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 all the way up to 9. Then A, B, C, D, E, F. And when we want to increment one more, since we're at 15, which is F, we're going to increment the next digit and reset the current one. So here. So this number in base 16 is 16. 1, 0. And then the next one we add is another 1, 2, 3, 4, blah, 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 all the way up to 19. And then 1A, 1B, 1C, 1D, 1E, 1F. And then 2, 0. And so on and so forth. Just like in base 10 and base 2, each digit, or place, is 16 times the last place. Remember in base 2, each place or digit was 2 times, and in base 10, each is 10 times. So here, the first digit is always 1s, and the next place is 16 times that, so we have the 16s place here, and then the next place that we have is the 256th place, and then the next place we have after that is 256 times 16, which is the 4096th place. And this is where hexadecimal gets a little brain warpy. You know, those numbers don't feel as comfortable as binary, where it's 1 or 0. You know, that kind of feels okay. And base 10 is obviously, very comfortable. They feel like nice round numbers. But hexadecimal numbers are round too, just round in their own way. All right, so let's look at some operations with hexadecimal. So I have a hexadecimal number here, 104A, and the place is marked here. I have the ones place, the 16th place, the 256th place, and the 4096th place. Let's convert that to base 10. What number is this if we were talking in, human speak? Just like base 10, we're going to take each number, add a place, and multiply it by the place value. So here we have a 1 in the 4096th place. So we're going to say 4096 times 1 equals 4096. We have a 0 in the 256th place. So we're going to do 0 times 256. In the 16th place, we have a 4. So we're going to do 16 times 4, which is 64. And in the ones place, we have an A. And this is where it'll get a little wonky. Remember that A is 10, right? Because A comes after 9. So, and all the way up to F. F is 15. So we convert that digit to decimal. So A converted to decimal, or base 10, is 10. So 1 times 10 is 10. And then we're going to add all those numbers together. And we get 4,170. So 4,170 in decimal, or base 10, is the same as 1,440A in hexadecimal. Though, nobody says it that way. We'd say 1040A or something. I don't know. Let's say we want to go the opposite way. We have a decimal number, and we want to convert it to hexadecimal. All right, so we have that same example that we had from the previous slide, 4,170. We want to convert that from a decimal number to a hexadecimal number. We're going to do it just like we did before. And these digits are the wrong places. I've corrected them on this slide. Sorry about the error on that last slide. First thing we're going to do is look at each place and see how many times that place goes into that number. So in this case, how many times does 4,096 go into 4,170? And the answer is 1. And if you're going to do this kind of math, you're probably going to break out a calculator, because these numbers aren't going to be terribly intuitive for most people. But anyway, we do the place times the digit in that place, subtracted from the number, and we get 74 as a remainder. How many times does 256 go into 74? The answer is 0. You can't pull 256 out, so we put a 0 in that place and just carry over. Then 16s. How many 16s go into 74? Well, 1 is 16, 2 is 32, 3 is 48, 4 is 64. So 64 is the answer, 4 times. So we take 4 times 16 and subtract it from 74. And we put a 4 in the digit here, and we have 10 left over. And then on the ones place, how many times can you pull a 1 out of 10? And the answer is 10 times, right? So we have a 10 here in the ones place, and the 10 written in hexadecimal is A. So we put an A in the hexadecimal place, subtract it out, and we always end up with 0. If you don't end up with 0 here, you've done something wrong. So that's how you convert the other way. So we take a decimal number and convert it to a hexadecimal number. Same thing as binary, same thing base 10, same rules apply. Just the value of each place and the values within each place. Alright, there's another one we're going to talk about very briefly, and it's called octal. Octal is base 8. Same thing as the other ones. Same rules apply. On octal, you roll over after 7 instead of 10 or 2 or 16. Similarly, when you roll over, you'll go from 7, then you'll increment the next place. So 7 goes to 1, 0. So this is an 8 in octal. And similarly, each digit or place is 8 times the previous one, and the first one's always 1. So the places that you have in octal are 1, 8, 16, and 512. Never use octal. Just don't do it. Nobody does it, and you're only going to cause yourself problems. But for completeness, most assembly languages and even a lot of other languages support octal notations, so it exists, but don't use it. All right, so wrapping this back to 6502. You know, you're here for 6502. Why do I care about all this math? It's going to be important. You know, having a fundamental understanding of how to do these conversions and understanding what a number looks like and how to switch the bases, because we all think in base 10, but the machine is either going to work in mostly hexadecimal base 16 or binary base 2. So being able to see those values, understand that they're not base 10 numbers, and convert them is important. In 6502 assembly, we designate hexadecimal with the $sign. So if a number is hexadecimal, we put a $sign in front, so $2F. In octal, we put a leading 0, and so it's 057. In decimal, there's no designator, it's just 47. And in binary, there's a % sign in the front. So percent 00101111. And if you did the math, which you didn't, but if you would have done the math on each of these, you'll see that each of these numbers above represent the same number. 2F in hexadecimal is 47. 057 in octal is 47. And 00101111 is 47 in binary. Right? But it's important to note, you know, those aren't the same. If you take a number, if you write a number 10 in 6502 assembly, just the number 10, nothing in front, the assembler is going to assume that is decimal. But that's not the same as $10, which is 16. Or octal 010, which is 8. Or binary %10, which is 2. So 16, 8, 10, and 2. All completely different numbers. Never use octal. The reason that you never want to use octal, as you can kind of see, this 0 out in front, a lot of people's minds will just make that disappear. They'll see 57, and it's way too close to a decimal number, and they'll think in decimal terms, oh, a leading 0 just doesn't do anything, right? This number is 57. This number is not 57. This number is 47 in octal. So just never use octal. Never use octal. Yeah. I think you get the point. All right. So we did a whole bunch of conversions from base 10 to base 2, base 10 to base 16, base 16 to base 2, or base 10. Now we're going to jump, you know, everything was to or from base 10, because that's, you know, what everybody's familiar with. Let's do a conversion from two uncomfortable ones. Base 16 to base 2. Actually, it looks like it's going base 2 to base 16, but we'll see. We'll see what happens. All right, so we mentioned this before. 8 bits called a byte. There's another name that we have that's called a nibble. It's a half a byte. It's a small byte. It's a small portion of a byte, right? Not a complete byte. So you get 2 nibbles out of each byte. A nibble is 4 bits. Important in some assembly languages. 6502, I think, less important. I don't remember there being any type of swap nibble instructions. But anyway, nice to know that it exists. Alright, so we are going to do a conversion from base 16 to base 2. I didn't mess up the slides again. We have a base 16 number up here. You can tell it's base 16 or hexadecimal because it has that $sign out in front, like we mentioned before, and that it has an A in it. Hexadecimal is the only one that's going to have an A of the ones we talked about. So hexadecimal A8, what is that in binary? Alright, so I'm going to do this in 2 chunks, each nibble at a time, because it's going to make seeing it on the screen just a little bit easier, and a bit easier to understand, I think, than having to multiply out huge places and stuff. So I'm going to break this math down into each place and then put them together. So as you can see, we have one nibble here that's A and one nibble here that's 8, and I've kind of color coordinated the bits inside the binary that represent the same thing. I've also put on a chart here, and we can do the mathematical conversion if we wanted to do the same thing that we did before, but you would have to say how many 8s, or how many 8s come out of 496th place. And that math actually works out really well because they're both power of 2s. But that's not the way, at least my brain, does binary and hexadecimal conversion. I find it easier to use these nibbles and just have this chart memorized. This chart is the same base 10 to binary conversion, but then converting over to hexadecimal. So 0 is 0 all the way across, 1 is 1, then binary 2 is decimal 2, which is also 2 in hexadecimal, and all those binary numbers are going to be the same all the way up to 9. You know, hexadecimal 9 and decimal 9 are the same. And then 10 in hexadecimal is A. And in binary, it's just 1 more than 9, so we add 1 here. And that carries over, and then we reset that place. And so this is A in hexadecimal, or 10. 8's place, right? 2's place. 8 plus 2 is 10. But hexadecimal doesn't roll over at 10, it rolls over at 16. So we have the A there instead. Same thing with the binary B for B. It's just A plus 1 and all the way down. And the last digit, F, is going to be all 1s because that's the last digit. If you add 1 more, they all roll over and you pop off 1 carryover here. And so I think memorizing this chart, valuable, and it's really only A through F that you need to memorize because the rest of them are the same for decimal and hexadecimal. Alright. So looking at this number A8 that we want to convert again, I'm going to do 1 nibble at a time, like we mentioned. So we take 8, we look up in our chart, 8 is represented here in binary, and so we just put that in that nibble right there. And, you know, obviously we can look at that and say, yeah, of course that's 8. That's the 8's place, the 4's place, the 2's place, the 0's place. So you got 1 8. All right, that all works. The next place we have is A. We just come over here, we find A in our chart, and slap that right in there, and you have A8. And that's all there is to it. So binary to hexadecimal conversion, you just memorize this chart or print it out. Really easy. It's actually way easier than the base 10 transitions. All right. So now that I showed you how to do all this mathematics by hand, I'm going to tell you you don't need to do any of this stuff. Use a calculator. At least if you're on Windows, just open up the Windows calculator. All right. It's going to do everything that you need for you. And so you might be asking, how do you do all this stuff? And the answer is, you probably never have gone up here in this dialog menu up here, but there's an option for programmer up here. You're going to select that option. All right. Then in that option, you'll see that it has hexadecimal, decimal, octal, and binary here. Boom. You'll see that decimal is defaultly selected. All right. To select a different encoding, you just click on whichever encoding that you want. You'll see when we click over to binary, all the numbers except 0 and 1 are grayed out because binary can only have 0 and 1, right? You see when we click over in hexadecimal, all of a sudden we have buttons over here for A, B, C, D, E, F, right? Because each digit in hexadecimal can go all the way up to F. So we need to be able to write each of those characters in here. You want to do a conversion? Let me show you. 47. I'm on decimal right now. So 47 47 decimal. 2F hexadecimal. 57 octal. Never use octal. And in binary, 1 0 1 1 1 1, just like we talked about before. Same numbers that we had on that slide. Right? If we have a hexadecimal number, let's say we're looking at a program and it has let's say CD, right? Has $CD. CD in decimal is 205. And here's its binary value. And that's all you gotta do to do any of these conversions. Adding 10 plus 10, right, is 20, right? 14 is 20 in hexadecimal. Same thing here. If we want to do 10 plus 10, well, we know 10 is A in hexadecimal, so A plus A equals 14. Same number, right? And you can see that it's 20 up there. So you can do any of the math that you want. You know, add, subtract, multiply, divide. Has shifting and other stuff here that I'm not going to cover. But yeah, just pull out the calculator. If it has a $sign in front, click over here on hex, and it says 20. You're going to notice from the $sign in front, that's not 20 decimal, that's 20 hexadecimal. But what does that actually mean? That means 32. And yeah, so you just use the calculator to go back and forth. Make it a lot easier on yourself. All right, so that's the calculator. Use it. So back at the original slide, at the beginning of the slides, we had this statement from the shirt and said, you know, there are 10 types of people in this world, those that understand binary and those that don't. And now we get it, right? Haha, in binary, this is 2. There are 2 types of people in the world, those that understand binary and that don't. But in 6502, we're going to put that %, right? Because if you write 1 0, that's actually 10. So you can laugh at all those programmers that wear that shirt, because every language that I know of, every assembly has a designator in front of the binary to indicate it's binary. So, you know, that shirt is kind of like stupid. But, you know, anyway. That kind of covers the introduction to mathematics in computer science that I wanted to cover. There's a lot more to it. We're going to cover some of it inside the instruction set when we get to those slides. Like I completely skipped over the shifting and all the logical operations, but we'll cover those when we get to the actual instruction set operations. I'm not going to cover them here. I really want to just cover the basic understanding of the different bases in mathematics, because I don't know that, at least public school system that I went through didn't cover those very well. Next session, we'll be covering a brief introduction to computer architecture. We're going to talk about how a computer works. And again, very introduction, 20-30 minutes of slides that are going to teach the basics that will help you understand how the instructions work and understanding the parts of the microcontroller, microprocessor, and how those instructions manipulate those to create operations. But understanding what parts and how the machine is built is kind of important to understanding how the instructions work, because the instructions are just telling those parts to do things. If you have any questions, if you have any feedback, feel free to drop them in the comments below. If not, I appreciate you watching, and good luck.